Welcome. If you've ever really wondered about the incredible dance of electricity that brings a car to life, well, you are in exactly the right place. Today, we're going to build that foundational knowledge you need to understand how cars get their power, from the classic combustion engine all the way to the EVs of today.
This question, it really gets to the very heart of every single gasoline-powered car on the road. Think about it. A small, simple box creates this massive spark that ignites fuel and gets thousands of pounds of metal moving. It's kind of crazy. And to really get a handle on the EV revolution, we first have to master the fundamental principles that make this incredible feat possible. Okay, first things first. Just like any technical field, electricity has its own language. To really understand what's happening under the hood, we've got to get fluent in the essential terms. This is the bedrock for everything else that follows. So let's dive in.
First up, we've got current, which we measure in amperes, or just amps. The best way to think about it is like water flowing through a pipe. It's the actual amount of electricity, the volume of electrons moving past a single point. So a higher current just means a whole lot more charges on the move.
Okay, so if current is the flow, what's pushing it? Well, that's voltage. You can think of it as electrical pressure. It's the force that's shoving those charged particles through the circuit. A tiny AAA battery might give you 1.5 volts of push, while a big EV battery can have 800 volts or more. And believe me, that difference in pressure is everything.
And the third piece of our puzzle is resistance, measured in ohms. This is basically the friction that electricity runs into as it's flowing. Every material has at least some resistance, and engineers actually use this concept all the time to control exactly where and how that electricity moves. Now, the cool thing is, these three ideas aren't just separate concepts. They're all tied together beautifully by what's called Ohm's law. As you can see in this super simple formula, voltage equals current times resistance. It is the fundamental rule that governs pretty much every simple circuit. You change one of those values, and the others have to respond in a perfectly predictable way. So we've got pressure and we've got flow, but how do we actually measure the work that's getting done? That's where power comes in, and we measure it in watts. Power is what you get when you combine the pressure, the volts, and the flow, the amps. It tells you exactly how fast energy is being used, whether it's to light up a tiny bulb or spin a massive electric motor.
All right, now that we've got the language down, let's see how all these principles get applied in the real world. We're going to look at how we store and direct all that energy using circuits and those little chemical powerhouses we call batteries.
So if you look at this diagram, you'll see there are two basic ways to design a circuit. On one side, you have a parallel circuit, which gives the electricity multiple paths to follow, kind of like a highway with multiple lanes. And on the other, you have a series circuit, which forces all the electricity down one single path, one component after another, more like a one-lane country road. This design choice has huge implications. And here's why that choice matters so much. In a series circuit, think old-school Christmas lights, if one bulb burns out, the entire string goes dark because the path is broken. But in a parallel circuit, if one bulb fails, no big deal. The others stay lit because the current just takes the other available routes. It's a really fundamental concept when you're thinking about reliability. Now, at the heart of any electrical system that isn't plugged into a wall is the battery. It's basically a self-contained little factory that converts stored chemical energy into electrical energy. It does this with a chemical reaction between a negative terminal, the anode, and a positive terminal, the cathode, which are separated by something called an electrolyte. And that reaction is what pushes electrons out into the circuit to do work for us. And of course, not all batteries are the same. You can basically sort them into two big families. You've got your primary or single-use batteries, like the alkaline ones in your TV remote, and then you have secondary or rechargeable batteries. This is where you find the classic lead-acid batteries that are in most cars, and the really powerful lithium-ion packs that run our smartphones, and of course, modern electric vehicles. So we've got all the fundamentals down. Now for the really cool part. Let's see how all this theory comes together in the absolutely fascinating, multi-step process of starting a traditional car. It's truly a symphony of mechanical and electrical engineering. It all starts right here, with the humble 12-volt lead-acid battery. This thing is the car's electrical reservoir. It just sits there, holding the initial charge needed to kickstart the whole operation. But here's the catch. 12 volts isn't even close to being enough to create a spark that can actually ignite gasoline. So the car performs this incredible magic trick using something called an ignition coil.
It takes that modest 12 volts and transforms it into a massive 40,000 volts. That's a voltage jump of more than 3,000 times, an immense jolt that's needed to leap across the gap in the spark plug.
And this right here is that mechanical dance we call cranking. First, the battery unleashes a huge surge of current to the starter motor. That motor then engages the engine's heavy flywheel, spinning it to get the pistons moving up and down. And then, as the engine turns, the ignition system delivers that 40,000-volt spark at the absolute perfect millisecond, igniting the fuel and bringing the whole engine roaring to life.
So the engine's running on its own now. The battery's big moment is over. For now, a different component has to take over all the electrical heavy lifting to keep the entire system powered up while you're driving. And that component is the alternator. It's connected to the engine by a belt, and it basically acts like the car's own personal power plant. It generates all the electricity needed to run your headlights, your stereo, the car's computer, literally everything. And at the same time, it's recharging that 12-volt battery, putting back all the energy that was used to start the car. It actually takes about a 20 or 30-minute drive just to replenish the energy from one single start. Okay, so we've just walked through a pretty noisy, complex mechanical process. Now let's shift gears completely and contrast that with the almost silent simplicity of getting an electric vehicle ready to go. And the difference, it's just night and day. A gas car has to be cranked. It's a physical, loud process to get a chemical reaction going. An electric vehicle, on the other hand, doesn't really start at all. It activates. You press a button and the high voltage system just turns on. It's ready to deliver power instantly and silently. So what makes this instant-on magic possible? Well, it's all orchestrated by an incredibly sophisticated computer known as the Battery Management System, or BMS. This is the brain of the EV's battery. It is constantly monitoring the health of every single cell inside the pack, checking voltage, current, temperature, you name it. It balances them all out so they work together perfectly, all while protecting the very expensive battery from damage and making sure you get the best possible performance and lifespan. And that really brings us to the key takeaway here. Starting an EV is deceptively simple. It's quiet, it's instant, but that simplicity hides a huge amount of complexity. While a gas car's challenge is that mechanical act of getting started, an EV's challenge is safely managing the immense and frankly dangerous amount of energy stored in its battery at every single moment. That's where the real complexity lies, and that is exactly what we'll be diving into next time.